Welcome to this talk about maximum clique in disk graphs. So this is a joint work with Edward Bonnet and Tim Hamilton. And here on this first slide, you can already see a disk graph, but let me start by defining what a disk graph is. So we consider a graph G, and we say that G is a disk graph if you can map the vertices of G into a set of closed disks in the plane, such that two vertices are adjacent in the graph, if and only if the corresponding disks intersect. So here we are given a graph G, and we can wonder whether G is a disk graph. And it is indeed, because we can find what is called a disk representation of G. So here, each vertex is mapped to a disk in the plane. For example, the blue vertex is mapped to this blue disk. And let's take a pair of adjacent vertices in the graph. Let's say, for example, the blue and red vertices. And you can see that indeed the blue and red disk intersect. On the contrary, if you consider the red and green vertices, they are not adjacent in the graph, and also the red and green disk do not intersect. So this is a valid disk representation of G. Then we can have some more constraints on our disk, and we can define what is called unit disk graph. So here the definition is the same, but the set of closed disks, they must have unit radius. Otherwise the definition is the same. And here this disk graph G, we can see that it is also a unit disk graph because it has what is called a unit disk representation. Okay, so let's go to maximum clique. And everything started in the 90s with this seminal paper by Clique, where they showed that it's possible to compute in polynomial time a maximum clique in unit disk graph, even and the algorithm requires a representation. So, for example, the input must be, let's say, for example, the position of the centers of the unit disk in the plane. This was extended later, 10 years later, by Ragavan and Spielrad, who found a polynomial time algorithm for maximum clique in unit disk graph, but which work even without a representation. Which means that the algorithm only takes as input an abstract graph and either outputs a maximum clique or a certificate that the graph is not a unit disk graph. So what we did and what I'm going to present in the next slide is a polynomial time algorithm for maximum clique that works in intersection graphs of translates of C, where phi is a fixed bounded convex set. And this works even without a representation. So to give you some more details about the proof, I'm going first to discuss this paper by Clark, Colborn, and Johnson. And in that paper, they have a key lemma that is as follows. I'm just going to read it with you. So we have two unit disks, D and D prime, with centers C and T prime. And we assume that these centers are within Euclidean distance, which is MD, which being at most 2. So in particular, it means that those two unit disks, they intersect. And then we consider the set of unit disks whose center is within Euclidean distance D of C and T prime. So if you want a geometric representation, it means that we are looking at the set of unit disks whose center is inside this lens here. And then the claim is that those unit disks whose center is inside this lens, it is possible to partition them into two cliques. And so I'm not going to go into more details, but what is important for us, what I want to insist on, is the fact that here you have this Euclidean distance, and here again this mention of Euclidean distance. And this is really important in the proof. Okay, so now let's go to our problem. And first, let us consider a set C that is bounded, convex, but as a start, let's assume that it is also centrally symmetric, meaning that there is a point in C such that there is a central symmetry around it. And then, if you think a little about it, you will observe that C induces a norm, by which I mean that there is kind of a corresponding norm to C. And in particular, if C is a unit disk, then the corresponding norm is just L2. And by that, I mean that two unit disks intersect if and only if their centers are within Euclidean distance 2. And then we could use a very interesting lemma that was proven recently by Armand et al. That says that if you are working with a bounded convex set S1, then you can find a bounded convex set S2, which is also centrally symmetric, such that GS1 is equal to GS2, where GS denotes the intersection graph classes of a class of translates of X. And this is how we could prove our theorem. So we start by considering C, which is bounded and convex. And then we know that we can find a centrally symmetric bounded convex set, C prime, such that the intersection graph class of C is equal to the intersection graph class of C prime. So it allows us to work with a graph that is, with a set that is bounded, convex, and also centrally symmetric. And from then, the idea is to follow the proof of Clark et al. And of Vagavan and Schminrad, but now we don't have we are not working with a Euclidean distance anymore, but with a distance that is given by any norm actually. So this is how we prove that, and we have a similar result that comes from this theorem by Bonamy et al. That says that there exists an efficient p-task for solving maximum clique in this graph, even without a representation. And so here, observe that we are considering this graph and not unit disk graph anymore. And so what we did is to extend this algorithm to homothet of C, where C is a fixed centrally symmetric bounded convex set. So before, our polytime algorithm was for translates, and now it's for homosets, which makes sense if you look at the results above. And here, actually, like, we really needed this assumption that C is also centrally symmetric. If it is not, then we don't know what to do. And the idea of the proof is, again, the same. We use the norm induced by C, and we try to follow the proof of Bonamy et al. And the idea of the proof is to show that there is a large class of graph that you cannot represent as intersection graphs of homosets of C. And so, if this class, as this class is large, then you know that the class of homosets of C is not too large, and then you can somehow show that there is an efficient p-task. Okay, so this is what I wanted to say for this positive result. But then the trial question that comes is, what is the complexity of maximum clique in this graph? And this is actually open since the 90s. Many talented people have tried it, and so far there is no answer. But I think most people believe that this problem should be NP-hard. However, there are some reasons to think that the known approaches to show NP-hardness to similar problems cannot be applied to maximum clique in this graph. So we need to come up with new techniques, new approaches, and to imagine these new techniques, to have some intuition, it's a good idea to think of similar problems. And this is what I'm going to present in the remaining of this talk, is this theorem here, where we could prove that maximum clique is NP-hard, and even AP is hard, in intersection graphs of unit disk and axis parallel rectangles. So such a graph can be, it's a class of graphs that have a representation like this. So you can see that each vertex is mapped into either a unit disk or an axis parallel rectangle. And then again, we have this intersection graph that is defined as before. And our result is maybe a little surprising, because we have seen that one can compute in polynomial time a maximum clique in unit disk graphs. And also, it was known since the 80s that you can solve maximum clique in polytime in intersection graphs of axis parallel rectangles. But here, what we could show that somehow, if you allow both in your representation to have unit disk and axis parallel rectangles, then the problem becomes NP hard and even APX hard. So, to show this theorem, we introduced a new problem that we call max interval permutation avoidance. And this, we could show that it is NP hard and APX hard. And now this may be of interest to you, even if you are not working in geometry, because this problem I'm going to present you right now, it's not really linked to geometry. Maybe you could be able to use it for some combinatorial problems which are not linked to geometry. So what is this problem? You are given a permutation of the integers between 1 and n, represented by some blue segments here. So for example, here if n is equal to 10, you have a permutation, and for example, this blue segment here means that 1 is mapped to 5 in the permutation, 2 is mapped to 3, 3 is mapped to 2, and so on and so forth. So as we have a permutation, we have 10 blue segments, length segments. And then also, as part of the input, you are given a set of intervals on the line y equals 1/2. So here you can see 4 intervals. And for example, the green one here is represented a little below, but this is just for sake of readability. And you should think of it as overlapping these other intervals. And then the objective and what you can do is, what you should do is to shift each interval vertically, either to the line above or to the line below. And what you want to do is to maximize the number of blue segments that will not be covered. So let me show you how this happens. For example, let's shift this red interval above. And here you can see that it's covering this blue segment here, this blue segment, and this blue segment. Okay, why not? And then let's shift this green interval then below. So, okay. And now, for example, you can see that this blue segment between 1 and 5, you can see that if we shift the orange interval below, then it will be uncovered. And we want to maximize the number of uncovered blue segments. So let's say we do that. And indeed, here you can see this blue segment here is uncovered. And whatever we do with the yellow interval later, this blue line segment here will still be uncovered. So that's good. And now let's, for example, consider these blue line segments between 4 above and 8 below. And you can see that if we shift the yellow interval below, then this segment, this blue segment, will be covered. So let's not do that and shift the yellow interval above. And here you can see that actually we are, like, this blue segment is uncovered, and there are also 2 blue segments which are uncovered. So in total, we have 4 blue segments that are uncovered. And if you take time to think about it, you can see that this is actually the optimal you can do if you want to maximize the number of uncovered blue segments. So, okay, this is the problem. And we could show that this max interval permutation avoidance that we call MIPA is NP hard and APX hard. And this holds even if you take some more assumptions. So for example, you can assume that the intervals have length at most 5. And also, you can assume that the blue segments here are symmetric along the line y equals 1/2. And by this we mean that in the permutation, if I is mapped to j, this is if and only if j is mapped to I. So here you have an example, because let's say 1 is mapped to 5, and 5 is mapped to 1. 2 is mapped to 3, and 3 is mapped to 2, and so on and so forth. So we could prove that this problem, MIPA, is NP-hard even on an APX-hard, even under these new conditions, these new constraints. So okay, this was for the MIPA problem. And now let's go to geometry. And let me tell you how we reduce this MIPA problem to maximum clique in this intersection graph class of unit disk and axis parallel rectangles. So here I have chosen to take a very small MIPA instance, and I'm going to tell you how we construct, how we reduce this MIPA instance to the maximum clique problem. So first, I'm going to define a set of points in the plane, which I will be using later to construct these axis parallel rectangles and unit disk. So again, we consider these points here, 1, 2 to 5 below, and what we do is we put them in a convex chain like this, a convex chain pointing towards the origin. So okay, we just do that. And then we take the central symmetry of each point along the origin, and this is how we find the position of the 5 points that we have above. So here, like, we have this central symmetry along the origin, and this is how I define the position of 10 points. Now, let me tell you how we represent the blue segment. And let's start by this blue segment here between 1 below and 5 above. And what we do is we define an axis parallel rectangle as the unique one that has as opposite vertices, one that is the point 1 below, and also the opposite vertex of the axis parallel rectangle should be this point 5 above, that is yellow. Then we do that for all blue line segments, and in the end we obtain these 5 axis parallel rectangles. And let me make the observation already that you can see that all rectangles contain the origin. And in particular, that means that any pair of rectangles intersect, which will be useful later. So it remains to tell you how we represent the intervals. And each interval will be represented by a set of 2 unit disks. So here we have this interval here that can cover the point 3. And what we do is we define 2 unit disks. Here, these red things should be unit disk. And actually, if you take a zoom here, you can see that we define this unit disk to contain the point 1, 2, 4, and 5, but not the point 3. And since this is a convex chain, actually, like, we take these 5 points to be very, very close, and then we can have this unit disk that is so huge it looks like a half plane, and it will be a kind of a half plane that separates the red point from the other ones. And this half plane of our unit disk should contain all points apart from point 3. And likewise, if you had an interval that would contain, let's say, 3 and 4, then you would take a line that separates the point 3 and 4 from the rest, and you would take a unit disk that contains the points 1, 2, and 5, but not 3 and 4. So you have such unit disk below, and also you have one unit disk above that is just a central symmetry along the origin. So now, to give you some an observation that will help to understand the proof that's coming on the next slide, we have this remark that what can happen if you want to shift the interval below, this will correspond to taking the unit disk below in the maximum clique. And then you can see that by construction, this unit disk here, it's not intersecting with this axis parallel segment here. So, which means that if you take the unit disk into the clique, then you will not be able to take the blue axis parallel segment into the clique because they do not intersect. Okay, so now I'm going to tell you the last details I want to tell you about the proof, how we do the reduction. So the first thing we do is actually we give weight 5 to the unit disk by actually placing 5 copies of them. So it means that for each interval in the input, we actually have 5 unit disks above and 5 unit disks below. Okay, and then we could show that in a maximum clique, the number of maximum disks is equal to 5 times the number of intervals. And even more, we could show that what you can do in a maximum clique is for each interval, you will either take all the 5 disks that are above or all the 5 disks that are below, which kind of correspond to this shifting of the interval above or below. And then in maximum clique, as all rectangles intersect, then you will take as many rectangles as possible. And the choice you can make is only decided by the choice of unit disk you have made before, because as I said, all rectangles pairwise intersect pairwise. And so finally, what we could show is that the number of rectangles that you can take in a maximum clique in this representation is equal to the optimal number of blue segments that you can leave uncovered in the MIPA instance. And this is how we could do the proof. So now I want to make an observation because we have this result for this intersection graph class, but why cannot do the reduction to maximum clique in this graph? And the reason for that is that if you take in the MIPA instance any 2 blue segments that do not intersect, you would see that in the representation we have some rectangles whose boundaries intersect 4 times. And by definition, in disk, like the boundaries can intersect at least twice, and this is somehow the reason why we don't know how to use this MIPA problem, or we can reduce it to maximum clique in this graph. Also, I can mention some more restrictions we can have on our set. And to show this theorem here, that maximum clique is APX hard in intersection graphs of half planes instead of unit disk. And this you can see by what I've said before. Actually, the only thing we need is to separate some consecutive points in a convex chain, and these half planes can do as well as unit disk. And also, we can replace these axis parallel rectangles by, we can assume that they are axis parallel epsilon squared for any positive epsilon. Because if you take all the points here to be very close together, and the same above, then you will see that these rectangles we have are actually epsilon squares. Okay, so I want to do now a summary of our technique. So here we have some rectangles that form a clique, and we have represented here the non-edges as dashed segment because actually there are many edges, so it's easier to represent non-edges. So we have the rectangles that form clique, unit disk that forms this anti-matching, and then each rectangle intersects with all other sets except for 2 unit disks, one below and one above. And why I wanted to do this summary is to tell you a little more why our technique can be is interesting. It's because there was already a known approach before that was called the code to subdivision approach, and which was used many times by many people. And I don't want to tell you and to give you too much detail about that. I don't have the time. But the thing is, the approach was very similar. You had a clique here and an anti-matching, but each element of the clique should not intersect with 3 elements of the anti-matching. And for us, it was only not intersecting with 2 elements instead of 3. And this is why our technique is actually easier to implement and to use as construction than the techniques that was already known. Okay, so this is a conclusion. We have shown these positive results here. We have some pretime algorithm for translate, an efficient pitas for homosets, and also we have this NP hardness that I've shown. And unfortunately, it's not possible yet to reduce the MIPA to maximum peak in pseudo disk. and so there is still space for improvement. Thank you.